Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Hello, I am Anya. Welcome to our show. Let's talk about physics.
Hello, I am Mateo. Welcome to our show. Let's talk about physics.
I was planning to talk today, in the sixth episode of this series, about quantum mechanics and Einstein's special theory of relativity. However, Mateo insists on talking about gravitational atoms. Therefore, we will postpone our episode about quantum mechanics and Einstein's special theory of relativity. Let's talk today about gravitational atoms. Mateo, please, could you introduce the topic?
Thanks, Anya. A gravitational atom is a hypothetical atom formed by two tiny, identical, and electrically neutral quantum particles with mass. One particle is fixed in a point. Like the electron in hydrogen-like atoms, the other particle moves around the fixed one. However, the attraction between the particles is not electrical but gravitational.
The math behind gravity and electricity? Just a constant sets them apart. Imagine estimating the quantum wave size in a gravitational atom, like we did for hydrogen-like atoms. As with hydrogen-like atoms, the wave should shrink to a point at a certain mass. This point marks the largest mass possible for a gravitational atom. It's a fascinating blend of classical and quantum physics.
Mateo, I agree with you. Assume the quantum wave associated with the mobile particle collapses, the gravitational atom would become unstable. Let's see the details of the calculations.
Imagine a quantum particle trapped in a box, the simplest model for spatial localization. Using a Grave de Peralta's equation, we find the positive relativistic kinetic energy. This energy is a rough estimate of the internal kinetic energy in gravitational atoms. For potential energy, we consider the negative gravitational potential. The total energy of the quantum particle with mass is the sum of kinetic and potential energies. The quantum wave size is estimated at the minimum energy level. This model offers a glimpse into the complex world of quantum mechanics.
Anya, I agree with you.
In 2021, a groundbreaking paper in the European Journal of Physics revealed a fascinating truth. Gravitational atoms with mass larger than the Planck mass can't exist due to quantum wave collapse. This wouldn't occur if the non-relativistic Schrödinger equation was applied. Relativistic kinetic energy is too low to balance potential energy in heavy gravitational atoms. In 2025, a paper on social media X, formerly Twitter, confirmed these findings. Grok, the AI of X, also validated this result, highlighting a quantum classical frontier at the Planck mass. The collapse leaves the quantum particle nude, transforming it into a classical particle. This discovery reshapes our understanding of quantum mechanics and classical physics.
Mateo, this is a sensational result and interpretation. This makes a theoretical prediction that agrees with a huge volume of observational and experimental data.
The Planck mass is nearly 22 micrograms, a tiny measure in the grand scheme of things. This means elemental particles, atoms, and molecules are quantum particles. Their mass is much smaller than the Planck mass. On the flip side, everyday objects like tennis balls, cars, and rockets are classical, their masses far exceeding the Planck mass. The same principle applies to cosmological objects and the universe, making them classical too. So, while the quantum world is tiny and mysterious, the classical world is vast and familiar.
Anya, you are very intelligent. Let's summarize our discussion today.
Like attractive electric fields, attractive gravitational fields can also spatially localize quantum waves. The total internal energy of gravitational atoms depends on the size of the associated quantum wave. Attractive potential energy is negative, but kinetic energy is positive. There is not enough kinetic energy in heavy gravitational atoms to compensate for the potential energy. This explains why the world of atoms and molecules is quantum, but we are surrounded by macroscopic classical objects. The fact that atoms and molecules are quantum, but macroscopic and cosmological objects are classical, supports the validity of Einstein's special theory of relativity.
Mateo, I think that we should talk about gravitational interactions of a quantum particle with itself.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.